I'm Calla. I'm a PhD student at the University of Melbourne, and I've been working with this really awesome group of people reconstructing the Paleo-Climate of Southern Australia during the Last Glacial Period. And we have some really interesting results about tropical moisture delivery across Australia during the period that humans were first settling the continent. So for some context, Australia is a really dry country at the moment, so 70% is defined as either semi-arid or arid. And our study site, Mares Cave, is right down south on Adnyamatnya country in southern Australia, and it sits on the boundary between the semi-arid and the arid zone. And today, it's way too dry for speleothem formation, so there doesn't appear to be any active speleothem growth, but it has these really interesting formations with a really distinctive bulbous shape to them. So for some context on how these grew, they began as stalactites hanging from the ceiling of the cave with a downwards direction of growth. But then at some point there was increase in water infiltration through the subsurface, which caused the groundwater level to rise, and the cave was flooded and the stalactites were submerged in groundwater. So from that point forward, they grew subaqueously while the cave was flooded. And so this subaqueous material has a radial growth direction, which is quite distinctive. And then at some point there was a reduction in groundwater recharge, which caused the water table to fall below the cave. And so then we see a hiatus in subaqueous speleothem growth. So that's when we see subaqueous speleothem growth, we know this is evidence that there was cave flooding at the time because of a higher groundwater table, because of more groundwater recharge. So essentially subaqueous speleothem growth we can interpret as evidence of a more positive water balance. And then when we see a hiatus in subaqueous speleothem growth, we know that there was no cave flooding because there was a lower water table and less groundwater recharge. So when we see a hiatus, it's evidence of a reduced water balance. So for some context on the aquifer that these speleothems grew in, so it's karstic and unconfined, and it's local-ish, so a few tens of kilometres squared. And it's actively recharged, and radiocarbon dating tells us that water has a mean residence time of about 661 years. And we know that the subaqueous speleothems precipitated from this groundwater, and we've confirmed this using trace element to calcium ratios, initial uranium ratios, and dead carbon fraction calculations. So these are our three speleothems that we've looked at so far, MC1901, MC2001, and MC2002. And they all have this internal stalactite component with a downwards direction of growth and different fabric texture, different color, different stratigraphy. And then they have this external section which is, has a radial growth direction, it's a different color, and the fabrics are really different as well. So here are our uranium thorium dating results from 3 pendulites. So we have MC1901 at the top, which sat highest in the cave, so it was only flooded by the most extreme cave flooding events. Then MC2001 in the middle, and then MC2002 down the bottom, which sat lowest in the cave, so it was flooded by pretty much all the cave flooding events. So we compared this to local summer insolation, and you can see that there's a broad trend for subaqueous speleothem growth to occur during periods of highest local summer insolation. So because I guess this relationship between summer insolation and moisture balance would be typically observed in a paleo-monsoon archive, we thought maybe this speleothem growth is being governed by the delivery of tropical moisture. So we said, is this tropical moisture delivery signal we're seeing? So we wanted to see if we could see a similar relationship or a similar signal on a millennial timescale. So we zoomed in, and we have all 3 pendulites growing during Heinrich 5. So our results from Heinrich 5 show increases in the growth rate in all 3 speleothems and increases in the initial uranium isotope activity ratios in all 3. And this is just a composite growth rate record from the 3 pendulites. So we interpreted these results as indicative of warmer and wetter conditions at the study site during Heinrich 5. So I wasn't sure how many speleothem people we'd have in the audience, so I thought I'd quickly run through our justification for these interpretations. So for growth rate, when we have warmer and wetter conditions, it means there's increased biogenic activity in the soil, so increased carbon dioxide production in the soil. So there's more bedrock dissolution and a higher dissolved load in the groundwater, which facilitates growth rate, faster growth rates. And then when we have increased groundwater recharge, we also have increased flow through the groundwater system. So we have this consistent supply of the reagents necessary for subaqueous calcite deposition. And then increased temperature also means reduced carbon dioxide solubility, so enhanced exsolution of carbon dioxide, triggering faster growth rates. When it comes to initial uranium isotope activity ratios, they can be considered a proxy for groundwater recharge, but their interpretation in subaqueous speleothems is opposite to the traditional interpretation in stalagmite or subaerial speleothems. And Kathleen Wendt et al. In 2020 published a really interesting article on this if you want to read more about that discussion. So if we think about our uranium decay series, or a trimmed down version, and we have uranium-238 with a really long half-life, decays to thorium-234 with a really short half-life, and then down to uranium-234. And if we think of our bedrock, and then we think of the bedrock being composed of grains and pore spaces, and then if you envisage this intersection between the grain and the pore space, so in our bedrock, after about 1.7 million years, we're going to have secular equilibrium between the 234 and the 238. But then over time, we'll have our 238 decaying via alpha decay, and that's a really highly energetic process. So it can actually thrust the daughter product out of the grain and into the pore space, and this causes damage to the crystal lattice. So our thorium-234, with its really short half-life, will pretty rapidly decay into uranium-234. And then when we have this process occurring over and over, then we end up with an accumulation of 234 in the pore space. And then if we have groundwater recharge, our pore space fills with water. We can also have leaching of the 234 via the damaged pore spaces into the pore space. Via the damaged crystal lattice. So if we think of our whole groundwater system, we've got our verdose unsaturated zone and our saturated phreatic zone. And then in a period of limited groundwater recharge, we have the accumulation of 234 in the pore spaces in the verdose zone. But then if we have a period of increased groundwater recharge and we have the local water table rising, it entrains all of this accumulated 234, and resulting in the 234 to 238 ratio in the groundwater increasing. So that's why when we see this uptick in the initial uranium isotope activity ratios in all three speleothems, we interpret this as indicative of increased groundwater recharge during Heinrich 5. So just to summarize, what we've got so far is enhanced groundwater recharge in southern Australia, most likely due to tropical moisture delivery during Heinrich 5. But I'm not the first person to identify this tropical response to Heinrich events. So we already know that we have intensification of tropical moisture delivery in response to both southern hemisphere summer insolation peaks and abrupt northern hemisphere cooling. But most of these studies are either within the modern monsoon domain or they're fed by catchments that are within the modern monsoon domain. So they can't really tell us much about changes in how far south monsoon rainfall can be delivered. So what's significant about our study site is just how far south of the modern monsoon domain it sits. So it's well beyond. It currently receives some tropical rainfall as extreme events. So low pressure systems can sometimes break off from the monsoon front and travel south over the continent. But most of the rainfall is actually received during winter off the Southern Ocean. So we took this to our climate modelling friends and said, are we crazy? Could we possibly have tropical moisture coming this far south? So they performed a hosing experiment. So Yan-Xuan Du and Josephine Brown used the Access ESM 1.5 model with 49K boundary conditions. And they introduced 0.4 Svei drops over 200 years to cause amok slowing. And they found, with the preliminary results, that there is an intensification of tropical rainfall across Australia during summer and a weakening of mid-latitudinal rainfall during winter. So this was pretty exciting. So to sum up where we are now, the implication of this is that if we have elevated groundwater levels in southern Australia in response to tropical rainfall, then that moisture has had to pass across central Australia as well. So if we're seeing elevated groundwater levels in southern Australia, then potentially we had elevated groundwater levels through central Australia as well. So what does elevated groundwater levels mean? Well, because we're really interested in groundwater, we think that it essentially translates to landscape transformation. So groundwater, being comparatively protected from evaporation, can supply perennial water resources, activations of springs and seeps, increased soil moisture, leading to increased vegetation abundance and increased primary productivity. So we think it's potentially pretty important, and we could have massive landscape change as a result of this influx of tropical moisture triggering groundwater recharge. So what is also pretty exciting is this pulse in tropical moisture delivery through to southern Australia actually coincides with when people potentially arrived in southern Australia around 48,000 years ago. So for some context on Australia, I wasn't sure how familiar everyone is with Australia. So we have our study site down there in the yellow box, and people most likely arrived to Australia possibly by that southern entry route there, and maybe also by the northern entry route, sometime between 72.7 and 59.3 thousand years ago. And they arrived in southern Australia by about 48,000 years ago. So this is the Wurree shelter, and it's just directly north of our study site. And so the route by which they went from northern Australia through to southern Australia is really debated. So as Renika was talking about yesterday, there's been this long-standing idea that Australia must have been more dry during the last glacial period than it is in the present, which led early theories to suggest that potentially Central Australia was a barrier to human movement, and people would have preferred to have moved along coastal routes before eventually moving inland. But as Renika was saying, there's actually some more evidence coming out to suggest that during glacials, the mid-latitudes of Australia actually could have been quite a lot wetter than they are today. So Bird et al. In 2016 looked at the distribution of modern water resources across the landscape from satellite observations, and they found that 84% of archaeological sites dated to beyond 30,000 years ago are within a day's walk of modern permanent water resources. So they concluded that during the late Pleistocene, when people were entering the landscape, the water distribution must have been somewhat similar to what we see in the present day. So this kind of set a precedence, and lots of modelling studies since then have also assumed the modern distribution of water across the landscape. So Bradshaw et al. Used the Love-Klim model to determine environmental carrying capacity, and they used a stochastic ecological cellular automation model, but they weighted their results by the distribution of archaeological sites. And then a companion article also assumed modern water distribution, but they modelled landscape, travel through the landscape between prominent landscape features via permanent water resources while minimising caloric expenditure. But they also weighted their results by their proximity to archaeological sites. But they still found a major corridor through the arid centre. So this one is a combination of the two previous ones, and they again found a major corridor of movement through the arid centre. And then most recently, Salas et al. In 2024 used the HAD-CM329 model output to drive landscape evolution, and the Love-Klim model output to determine ecological carrying capacity. But as opposed to the previous ones, their results weren't weighted by the distribution of archaeological sites, but they still found preferential movement through the continental interior. And they asserted that their predictions could possibly be improved if they were to incorporate hydroclimate reconstructions from localized proxies of hydroclimate. So to sum this up, people can definitely live and thrive and survive in really water-limited environments, but the availability of potable and interconnected water resources does influence how people choose to move through the landscape, especially if they're travelling through an unfamiliar environment. But most of these models do assume the modern distribution of water despite different boundary conditions, and despite research suggesting that Australia was very different climatically then than it is today. Despite this, most of these models do see some degree of movement through Central Australia, possibly governed by the distribution of archaeological sites. And so perhaps if we did see a pulse of tropical moisture coming through Central Australia around this time, it could explain the distribution of archaeological sites and maybe suggest that the continental interior was equally as favourable for people as the coastal routes would have been. So to summarize this, we think that perhaps Heinrich 5 triggered a pulse of tropical moisture through central Australia and could have catalyzed landscape transformation through the continental interior around the same time that people were arriving, which could have implications for the landscape, differences between coastal interior routes and how people would have chosen to move through the landscape. Thank you.